So obviously I'm not in class today, but I wanted to still move forward with our content. So one thing that you'll learn is that when I know I'm going to be out of class, I make videos to help you move forward in class and help explain some of the difficult content. So this is the first one, and this is on 5.2 on the greenhouse effect, which are the notes that you're supposed to prepare for today. I hope that you all took the weekly quiz that was due last night at 11:59 p.m. Um, and I wanted to take a moment to let you know that there's a new weekly quiz up. And just to get caught up and give you a few more grades, it is due by this Saturday at 11:59 p.m. And I'm taking the best score. It's open note, not open person. So you may use your own notes or resources, but you are not meant to talk to other people. The idea is that this is practice, getting ready for a larger unit test or quiz. So that being said, let's move forward. Here are the 5.2 learning statements. I've written them out as 5.2.1, point 2, point 3. I'll scroll down a little bit here, all the way down to the point 6. And so I'm going to go through these fairly briefly, but this may be one of the longer videos, given that you do have 90 minutes to watch, listen, take notes, and answer a few questions in the assignment that I've shared with each of you. That will be withdrawn from your editing rights will be taken away at the end of the block. So you want to make sure you get through this in a timely manner and you answer the questions. Okay, so that being said, let's start. So the first bullet here is draw and label a diagram of the carbon cycle. So what I typically do, and I see that you do this on your note sheet, is go through and identify each of the command terms before you get started. I'm going to do them as we talk about each of the notes. So I'm going to underline the command terms, draw and label, which is kind of redundant. IB, for whatever reason, will repeat them, but that's fine. So draw is to make a diagram, right, with pencil lines usually. Make a diagram and label it. Now, they're reminding you to label it, but make a diagram and label the carbon cycle to show the processes involved. So that's exactly what we're going to do. I'm just going to scoot a little bit over to the right and add my drawing. And so oftentimes we think of atmospheric carbon dioxide first, so I'm going to put that here. You also have a diagram of this on page 133 of your textbook, but I'll tell you there are some limitations, as you probably saw in the limiting questions. There are things that I want you to note that are missing from this diagram. But we've got atmospheric carbon dioxide, and you should know that CO2 gets pulled out of the air into producers. You could also write the word autotrophs, which maybe is a new word for you, maybe, hopefully not, but it could be. But you can think of plants. But there are many protists, and we'll learn about that. So there are many protists that are photosynthetic, as well as some bacteria. But anyways, they're all producers because they're using sunlight and the atmospheric carbon dioxide to turn that into sugar, which then goes on to the carbon that's found in consumers. So let me just take a second to back up here. So we're talking about carbon here, okay? Looks a little bit like the food web if we replace this with sunlight, but we're really talking about the carbon cycle. So there are a couple nutrients that we're going to talk about a little later that contain carbon and that this carbon dioxide gets turned into. So I'm going to make a list over here just so you have this as additional notes and to foreshadow what we'll talk about later this year. Carbohydrates, lipids, proteins, and nucleic acids. So these are all the molecules. Some of them are energy energy storers, but they have many, many functions. And these are the molecules that the carbon travels through. So producers make some of these molecules, particularly carbohydrates and lipids, from the atmospheric carbon dioxide, and that gets passed up to the carbon in the consumers, which then throw back out to the atmospheric carbon dioxide. But there's an error that, there's another error in the book that says that if the producers catch on fire through combustion or the forest fires, carbon dioxide is released into the atmosphere. I'm going to add yet another arrow back. This is the arrow that's missing in one of the leading questions. I guess I should go ahead and start labeling. So, atmospheric carbon dioxide goes to producers through the process of photosynthesis. So remember that the command statement is to draw this carbon cycle and label the processes. So photosynthesis takes carbon dioxide out of the air into producers. Then we've got feeding or consumption as the process that take from producers to the carbon in consumers. The consumers breathe it out in cellular respiration back to the atmosphere. And the process, the organelle that producers have, many producers, plants do, not all photosynthetic organisms do, that these consumers also have is the mitochondria. And the mitochondria also is the one that does most of the work for cellular respiration. And so producers can, they don't necessarily always have this arrow, but there can be an arrow from plants, if these producers are plants, back to the atmospheric carbon dioxide. The other thing that adds carbon dioxide to the atmosphere is when there's death, and the carbon goes to decomposers. So there's death. But let me just point out that's also true for the producers. So if the producers died, the decomposers go at them and take the carbon dioxide, and the carbon dioxide goes back to the atmosphere, also through cellular respiration, and sometimes the carbon decomposers, and this is labeled in your diagram, is partially digested, and it actually gets preserved as fossil fuels. Hopefully you've heard that word before, but think of like gasoline. So these decomposers the carbon decomposers don't always get broken down into cellular respiration. Sometimes they get stored in these fossil fuels deep under the earth, and that carbon in the fossil fuels, at least for the time being, due to human impact, combustion by humans. So by human impact, we're burning these fossil fuels and reintroducing carbon dioxide into the atmosphere and driving this process, for the most part, forward, but really increasing the amount of carbon dioxide in the atmosphere. I'm sorry, I apologize, I'm moving a little slow. It's really early in the morning. I'm recording this for class, but I'm really trying to think through everything I say before I add it, and I'm staring at this arrow and trying to remember why I drew this. And I just remembered. So combustion by like forest fire. So this would be a natural process that's closed. This process that we take some of these fossil fuels and throw them back into the atmosphere, carbon dioxide, is not normally part of the equation because this carbon was removed by the fossil fuels into making the fossil fuels. Alright, so that's a pretty complicated process. There's a lot that I talked about that's behind this. There's a lot of background that you may not know quite yet. For example, that these nutrients really cycle back and forth here, but that carbon is what gets converted time and time again back into the carbon dioxide that we breathe out and that plants use to turn into sugars or fats or proteins or nucleic acids. Okay, so I think that's that. Let's go back. That's point one. So it took a little while, but that's okay. Let's keep going. So point two is analyze the changes in concentration of atmospheric carbon dioxide using historical data. So we need to look at the word analyze just to make sure we know what we're doing and what we're being asked to do. So point two, again, says analyze, and analyze means to, let's see if I've got my pen working. Yeah, okay. Interpret, essentially to interpret data, to make conclusions. So we're going to be interpreting data to make conclusions about the changes. This is my changes in concentration of atmospheric carbon dioxide using historical data. So it tells us what data we're going to use. I'm not going to draw it up here or throw a picture in here, but it's on page 134. And I think that the section actually does a pretty good job of explaining what's going on, but there are a couple questions I'm going to throw at you. So I was just thinking about this when I was talking. I want to come back to this idea here, right here, the combustion by forest fire. In fact, that's not always a natural process. It could be just by fire, but when we burn wood in the winter when it's cold, we're doing that for the heat, but by burning wood that's full of carbohydrates, cellulose, we're actually releasing that carbon dioxide back into the atmosphere. So this could also be a human impact. But this is the larger one, which we'll talk a little bit more about, that increases the amount of carbon dioxide in the atmosphere. Actually, that's a good idea would be to put stars next to the human impact ones. So it could be this one. And then there's another one that also is quite large. And we might think of this as, well, of course, consumers give off cellular respiration. But the human impact here would be in farming, in agriculture. By having more consumers, like more cows or pigs or chicken, are we increasing the amount of cellular respiration that's happening, therefore increasing the amount of carbon dioxide that's being put out into the atmosphere? Just a question for now. We'll talk a little bit more about it soon. All right, so back to point two, which is to analyze data. So what I want you to do is to think a little bit about the difference between patterns and trends. I don't know why I did one in caps and the other one not, but I want you to be able to tell me the difference between patterns and trends and then apply that idea to the graph on page 134. So I want you to be able to describe to me the pattern of the carbon dioxide concentration in parts per million over the last 50 or 60 years, as well as the pattern, the trend in the pattern, and come up with an explanation for the patterns. They're actually explanations, so there should be more than one thing that you could attribute to the pattern that you see repeated over and over and over again in that graph. If you need a textbook, there are a couple on the bookshelf. Share that around. Make sure that you understand the difference between these patterns and trends. Okay? So that's all I'm going to say about that. Okay, so that was much faster. That was much quicker. Okay, so we got point 3, which says to explain the relationship between rises in concentration of atmospheric carbon dioxide, methane, nitrogen oxides, and the enhanced greenhouse effect. Okay, so let's look at the word explain. So explain means to give a detailed account of causes, reasons, and mechanisms. So we're going to talk about the relationship essentially between atmospheric carbon dioxide, methane, nitrogen oxides, and this other idea, the enhanced greenhouse effect, which is a really important idea that IB often asks about, so we'll spend a few minutes talking about this. So I don't think the greenhouse effect is really anything new for you, and if it is, then I'm going to leave that to you to figure out, but it's outlined on the bottom of page 135, and I'll just briefly go over it. Essentially, sunlight enters our atmosphere through space, and most of that sunlight reflects off the surface of the Earth and travels back to the atmosphere, but we have an ozone layer, which includes some oxygen, some O3 or oxygen, special kind of oxygen molecules. But we've also got water and carbon dioxide that prevent all of that energy from radiate or bouncing back into space, which is good because we actually need our Earth to be a relatively stable climate for us to survive. If it fluctuated up or down, or was at a lower temperature, then we wouldn't survive today. And in fact, evolution might be very different. A different organism, if anything at all, would be alive today in our place as well as in the place of many, many, if not all, other organisms. So remember, temperature is one of those abiotic factors that help support an ecosystem. So it's important to maintain a pretty constant temperature. Of course, our temperatures can fluctuate. Think about our winter and our summers. Those are extremes. But it's still a relatively minor set of changes in temperature. But anyway, some of that light energy that comes in from the sun is turned into heat energy, which warms up our mountains, oceans, forests. That's what it says in the book. And the greenhouse gases like water or carbon dioxide, and also we'll talk about methane and nitrogen oxides, trap some of that heat in the atmosphere. And that means that our Earth's ecosystem is warmer than outer space because we can keep that energy and build it up here on Earth within our ozone layer. So that's the greenhouse effect, which is not a bad thing. Oftentimes people talk about the greenhouse effect and associate something bad. The regular greenhouse effect is not a bad thing. The enhanced greenhouse effect is a different story. So I'm going to talk about that. So normally the amount of carbon dioxide in the atmosphere is relatively low, and water we really have no control over. We need water. So water is one of the most powerful greenhouse gases that prevent heat from being lost, but we can't do a whole lot about it. So we'll talk a little bit about carbon and the enhanced greenhouse effect. But let me just point out and read the second paragraph to you on page 136. It says, climate experts have confirmed that Earth is undergoing global warming because of an enhanced greenhouse effect, also known as the runaway greenhouse effect. Increasing levels of the main greenhouse gases caused by human-generated pollution are causing the atmosphere to retain more and more heat. So that's the overall idea, and what we're doing here is outlining how each of the gases um, impact this. So we're going to talk about carbon dioxide, methane, and then oxides of nitrogen. Um, so let's talk a little bit. Let's talk first about um, nitrogen oxides, because you probably know the least about these. Sorry, I was just thinking about which one I wanted to start with there. Nitrogen oxides. So you need to know the word nitrogen oxides, not just nitrogen gases. You need to know nitrogen oxides. It's a specific type of nitrogen gas. And essentially, the idea is that as human population and needs increase, so do the waste gases that are produced. For example, by burning more fossil fuels. And you're probably thinking alternative energy. That's what the buzzword is now. Also using organic, which just means carbon-based, not that it's good, but organic is carbon-based, and commercial. I don't know why I put an F there. Commercial fertilizers to help crops grow, and many other industrial processes. So without going into any detail, IB just needs you to know that. Industrial processes. These all add nitrogen oxides to our system. We've also got methane, which is another greenhouse gas, which is CH4, if maybe you remember that from chemistry, maybe you don't. But the C is the carbon in CH4. And actually this is one that is in some ways a larger concern than CO2. But people don't really talk about it. And we'll talk about why. Okay, so methane increases mostly because of cattle ranching. So cows make an incredible amount of methane. There's also a lot of it that's made in waste landfills. So by bacteria that are breaking down or decomposing. And in making natural gas, which is methane. So making it and really distributing natural gas. So whenever there's a break in pipes or anything like that, we were losing. So what's interesting is that as human populations increase, there's more need for food and dairy. Well, people think so. This is Mr. Patel, the vegan, talking. People think that those things are needed, but really what ends up happening is that methane increases. And the reason people don't really talk about it is because it's very hard to give up what we hold to be our cultural norms. So if you grow up eating meat or dairy, it's very hard for someone to consider not eating those things anymore. Because if I were to tell you to stop eating that, you might be thinking, well, what's left to eat? You might ask, Mr. Patel, what do you eat? Right, because it's such a different idea than what you grew up or what you already do. But the amount of animal products that we use, particularly in the United States, increase the amount of methane gas in the atmosphere. And methane as a greenhouse gas traps more heat, and as a concern, as the human impact component of this, really all of this, as far as the human impact, we would call this the enhanced greenhouse effect. The human impact is the enhanced greenhouse effect. Enhanced greenhouse effect. So you should know the difference between the enhanced greenhouse effect and the greenhouse effect. The enhanced greenhouse effect is the human impact, and you should be able to outline these things. I did talk about carbon dioxide because all of this is also related to carbon dioxide as well as burning fossil fuels. So there's quite a bit here that we're doing that we don't often think about. So, and one thing that I realized that I should say is that as a vegan, I don't participate in the cattle ranching, but I still throw things away, and I use energy. So I use quite a bit of technology. For example, I'm recording this video, which means that my computer and everything else, all my peripherals are plugged into the wall, which you might not think about as an energy source, or maybe you kind of do, but here in Virginia, the energy is probably coming from coal. That coal is a fossil fuel, so even as I talk about reducing carbon dioxide emissions, I'm inherently using that. So we're all guilty of it, particularly here in the United States. We have a high carbon footprint, but there are ways that we can minimize our human impact on our atmosphere and our environment. So, okay, I think that covers it. So we're getting close to the end here. Let's see. Point 4, outline the precautionary principle. Now, I hope this is ringing bells in your ears right now, because that's something you have to do for your group 4 project, is talk a little bit about the precautionary principle. You have to outline. So, what does the word out mean? So, it means to give a brief overview. So it's not just listing things, but talking about them. So I'm not going to go write anything down because I think we can talk a little bit about this. So the precautionary principle is simply the idea that it's better to be safe than sorry. So we don't really practice this very much in the United States because, well, think about this. So you know the history of smoking cigarettes. We know that they're bad for you now. We've known that they've been bad for you for a long time, but we worry about that after the fact. And so now, after the fact, we look for modifications or changes or treatments to a lifetime of smoking rather than being preventative of that from the beginning. So I'm going to read to you the second paragraph on page 138. How there are many warning signs that lead experts to invoke the precautionary principle. This is an ethical theory which says that action should be taken to prevent harm even if there's not sufficient data to prove that the activity will have severe negative consequences. It also stipulates that if people wish to engage in activity that might cause changes in the environment, they must first prove that it will not do harm. So if you think about that, we don't do that in the United States. Other countries do, though. And I would say that this is probably a very good idea, because if changes are made and negative permanent changes are made, then it's very difficult to restore them. So think about we talked about food webs in class last time. If one of those populations were to be wiped out, what impact would that have on the rest of the populations? And it's not so easy to reintroduce a population back into its environment, particularly because there's been a new balance struck, or a new balance in that ecosystem, or the entire ecosystem has been wiped out. So I want you to think a little bit about how the precautionary principle should be invoked and how we might better be able to follow it. Again, to be safe, better to be safe than sorry. In some ways, people feel that they're being found guilty they start out guilty and have to prove their innocence by demonstrating that their action will not harm the environment. But from the other perspective, it's probably a good thing to be able to say that my actions as a business will not impact the environment negatively. So I'm going to leave you to evaluate the precautionary principle as a means of strong action in response to threats posed by the enhanced greenhouse effect on your own, as well as point 6. But I'll tell you that for point 6, there is a list of 5 things that you should know on page 140, but you need to read that entire section. That is a heading of human impact on Arctic ecosystems. It's not so easy. You're not going to earn the points by saying the Arctic ecosystem will be in trouble. You need to outline. You need to give a brief summary or brief. You need to be able to discuss this concern particular to Arctic ecosystems. Now, why Arctic ecosystems? Why not our local ecosystem? I have no idea. But the Arctic ecosystem is part of our curriculum, so you want to make sure that you understand that, and you know how the enhanced greenhouse effect, even local, even in the United States, would impact a global ecosystem or an ecosystem somewhere else in the world. So our actions impact our own environment as well as others, and others' actions impact us as well. So how might that take part in the precautionary principle? Anyways, watch this, answer a few questions in your Doctopus, and then start answering the question, or start completing the objective sheet for the next section, which is 5.3, and take the weekly quiz that's due Saturday night at 11:59.